Hey guys, welcome to Earth Science. We may have to pause a few minutes if we let some more students in. How you doing today, Mr. Muse?
Just fine. Yourself, sir?
Excellent. Thank you. Thank you. So we've been talking about the different positions of the Earth and the Sun and the Moon in the sky. And we're working on that sheet there, the 6 questions with the comments. And the first one says, is the Earth tilted towards the Sun or away from it during the spring? And what evidence do we have? Well, we know that the Earth sits on 23.5 degrees tilt, right? And in the North Pole tilts towards the Sun, we have summer. When the South Pole tilts towards the Sun, we have winter. We are actually, as an Earth, closer to the sun in winter, but our northern hemisphere is tilted away, so we get winter. All right, so the Sun and Moon provide us with rare, beautiful displays. What could that possibly be? Like tonight, the supermoon, when the sun rises and sets, and the big ones are eclipses. So is the gravitational pull of the Sun stronger than the gravitational pull of the Moon? Well, the Moon causes the tides, but the Sun is 177 times greater gravitational pull. So a single revolution of our planet around the Sun takes 365 and a quarter days. Is this a statement of fact or an opinion? How do we know? Well, we know it's a fact because all the ancient calendars had a common 365 and a quarter, or a leap year in some ways. They were all common. And the ancient astronomers would stay up all night, night after night, year after year, tracking the movement of the stars. All right, so the main idea of the tides, there's 3 details that deal with the tides. And everybody knows the Moon. Sun has some, but what's the other thing that's a major player in it? The Earth. So when they line up, Sun, Moon, and Earth, or Sun, Earth, and Moon, you get the greatest pull on all of them. Excellent. So why is it important that we include a leap year in the calendar? Because we would lose 6 hours or a day every year, but we would lose 6 hours every year. We'd start before it completed its revolution. Excellent. Guys, I want to share a quick video with you.
Imagine that you live in North America, and one day you call your friend in Australia. You guys are talking, and you make plans to go visit him next summer.
So, anytime next summer works for you? Yep.
In a few months, July rolls around, and you hop on a plane for your Australian vacation. Imagine your surprise when you show up at his house, and he tells you,
"What are you doing here, mate? It's the middle of winter."
and then you say,
Winter? Summer back in America.
and your friend's like,
I don't know what to tell you. July is winter for us.
Okay, I don't get this. How can it be summer in America and winter in Australia at the same time?
that's a great question. I think we can help you out with that. To answer this question, we have to zoom way back and start with a top-down look at the Earth's orbit around the Sun. Oh, by the way, everything you see in this video isn't to the correct scale. Now, the Earth's orbit isn't a perfect circle. It's actually an ellipse. You usually see it drawn like this. Lots of people think,
Hey, this must be why we have seasons. When the Earth is close to the Sun, we have summer. And when the Earth is far away from the Sun, we have winter.
but that's actually not true. If that were true, it would be summer in America and Australia at the same time.
And we know that's not the case.
Exactly. The way we've drawn Earth's orbit here is really exaggerated. People just draw it that way to highlight the extremes. In actuality, there's a relatively small difference between the Earth's closest and furthest points from the Sun. If we draw Earth's orbit with the correct shape, It looks like this. You can see it's actually pretty circular, but it's not perfect. So it's not the closeness of the Earth to the sun that causes the seasons. To see what's actually at work, we have to look at the orbit from the side. In our side view, the Earth is revolving around the sun in this orbital plane here. It takes 1 year to go through a full orbit, 365 days. Remember, at the same time, Earth is rotating on its axis once every day. The important thing, for the seasons at least, is that the Earth actually isn't straight up and down. It's tilted at an angle of 23.5 degrees. So when the Earth is on this side of the sun, the northern hemisphere is angled away from the sun. The southern hemisphere is angled toward the sun. When the Earth is revolving around the sun, it stays tilted in the same position. The axis doesn't wiggle around or anything. It just stays fixed in a certain direction. So when the Earth is over here, the northern hemisphere is angled towards the sun, and the southern hemisphere is angled away. When a hemisphere is angled towards the sun's rays hit it directly. That's what's happening in the northern hemisphere here. But when a hemisphere is angled away from the sun, like the southern hemisphere here, the sun's rays hit it indirectly.
Okay. So what difference does direct or indirect sunlight make?
Oh, there's a huge difference. Let's take a look with a simple experiment. In this experiment, we're going to use a flashlight to simulate the sun. Say that the flashlight is a particular sunbeam. If it's shining directly, all its energy is concentrated in a certain area. But if the sunbeam is shining indirectly, the area is larger. This means that the same amount of energy is spread out over a larger area. So, in a particular point on the paper, it feels colder in the indirect sunbeam than in the direct sunbeam. And the more indirect the sunbeam, the larger the area. It's important to note that the amount of energy in the sunbeam is always the same. It's not changing. However, if it's spread out over a larger area, we feel it less. Let's take a look at what this means for the Earth. Here we have a globe that's angled at about 23.5 degrees. It's June, so the northern hemisphere is angled towards the sun. If we shine the flashlight directly on the northern hemisphere, we see it illuminates a certain area. But when we move the flashlight to shine indirectly on the southern hemisphere, we see that it's illuminating a larger area, just like we talked about. So let's put it all together. When the northern hemisphere is tilted towards the sun, it's receiving direct sunlight. It feels warmer, which means it's summer there. And the southern hemisphere is receiving indirect sunlight, which means it feels cooler. That's winter. 6 months later, when the Earth is on the other side of the sun, we have the opposite. It's the southern hemisphere receiving direct sunlight, so it's summer there. And the northern hemisphere is receiving indirect sunlight, so they're having winter. And now you know the reason for the season.
Awesome. So it's not how close the Earth is to the sun that matters, but instead it's the tilt of the Earth.
Which is also why it's winter in Australia at the same time as it's summer in America.
You got
Excellent. All right, guys, any questions? All right, that's going to wrap it up.